So recently we had a visitor or subscriber, I believe from England, asking about these guys. These are live fiber identifiers or live fiber detectors, and they have some pretty specific uses. And their question was, how far can we use these to identify a fiber or use them as a quote-unquote fiber toner? We're going to look into that in this video, so stick around. I'd like to start out by welcoming our new subscribers. We appreciate you joining the channel and the community. If this is your first time visiting, we hope you find the information useful and would consider subscribing to the channel. It helps us out. So as I mentioned in the intro, one of our subscribers, and I believe, like I say, they're in Great Britain, we were talking about visual fault locators and using those to identify fiber. And then we were talking about, in the comments, we were asking about live fiber identifiers utilized as toners. So again, this is something that we use out in the field to help us identify before we go splicing or cutting a fiber if that fiber actually has traffic on it, right? Obviously, we don't want to start disrupting service when we're doing our splicing. So these guys operate on a controlled macro bend. So as you put the fiber into it and close the gate, it will put a macro bend in to the fiber. Some light escapes out. Again, the same as doing a macro bend on a jumper, right? As you put the visual fault locator, you can see some red light there escaping, and it will read that light, and it's capable of telling you that there's traffic on there. Okay, so one of the things about these, there's a lot of conversation as we do certification training and fiber training and stuff. There's some very specific, how do you say, opinions on these, right? And some of them have, like this guy here, just shows you traffic and which direction the traffic's coming from. And then this guy would show you traffic, which direction it's coming from, and an estimated power level, all right? And then this guy also does the same thing. So this is a Viavi or JDSU. It's a little bit different than these guys. This doesn't require these little sleds. So these come in different sizes. So 3 millimeter, 900, 250, etc. And that's how we control the macro bend. This guy, you just drop the fiber in there, pull the trigger, it closes the gate in here, and then it puts in the macro bend and it reads. You can separate the lower part and just use it kind of as a pocket power meter. Okay, so it's kind of a cool little device. Pluses, minuses. This guy has a larger head, obviously, than these guys. So if you're doing splicing and you're trying to get onto a short fiber in a tray where you don't have a lot of room to work, then it could be a little problematic. The plus on this is I've tried to break fibers with this guy and I was unsuccessful. I mean, it's pretty forgiving. Whereas these guys, if you don't set the fiber correctly and not paying attention, it's pretty easy to, when you close this gate, that it will actually break the fiber. So you want to be careful with this. One of the things we want to talk about on these guys is this one doesn't show what direction the light's coming from. And I don't really care personally because, I've had guys, we absolutely get in some wonderful heated discussions on it. But the traffic, if it shows you what direction the traffic's coming from, it doesn't matter to me because currently, we're not only using, fiber 1 and 2 for transmit and receive, but we're also using what's called bidirectional optics, right? So coming from side A, it's squirting out 1550, and coming from side B, it's squirting out 1490 on the same fiber. So we're doing wave division multiplexing on a single fiber. We get transmit and receive at different wavelengths, right? So when you put this on there and you have bidirectional light, I mean, it's firing both directions simultaneously, and you put this on here, it's going nuts. It's telling you traffic's coming from both sides. So again, you know, it's the primary purpose of these is really to tell you that there's light on the fiber before you break it. One of the other things, I'm trying not to be mean here, but a splicer was actually taking one of these and putting it on each side of the splice sleeve, trying to see what the splice loss was based on this. And this is not really super accurate. And I've got a little test bed thing here set up so we can see what's going on. We'll go to our power meter over on this side. Okay, so we have our power meter set up. It's set in dBm. We know this guy here is launching out at a -7 dBm, so these are absolute values, right? dBm is referenced to 1 milliwatt of power. Therefore, it is an absolute value in measuring transmit power from the actual laser, all right? The difference between side A and the measurement at side B, if it was -7 dBm and then -8 dBm, we'd have 1 dB or a relative value between the two in loss. So this guy here, let's go ahead and we're going to just pop this in here. And let's turn on the laser. Okay, so right now it's -716. So we'll take the 1/10 of a dB for connectors and fiber and things like that. We'll grab this somewhere in the middle. You throw this into your sled. Now there's a groove. There's a groove in here, right here, that this will sit into. Okay, and that's kind of, you got to pay attention to that. Hold that down. Pop this up, and now it's showing that traffic is going this way. So from our light, and if we kind of get our cords all untangled here, we can see, you know, it's coming in on this side and then going out and being read over here. This is reading a -24 dB. So the question is, when it takes this value, what is its reference point, right? In other words, dB is a relative number between two absolutes. So where did we get the absolutes to derive this number from? Does that make sense? Hopefully it does. So again, this is just a, you know, it probably would work. Let's see if we can do a macro band here. Yeah, see, so if we throw in a macro band, we got a change in the value. It went down 1 dB, which is, you know, not a bad macro band. But again, this doesn't correlate to the actual power, right? So it's not really useful. One of the other things that we can do with this is, if you have a light source that you can modulate, you know, change the frequency on, these guys will read whether it's 270 hertz, 1 kilohertz or 2 kilohertz. So as we hit this modulation button up here on the screen, we can see it's 1 kilohertz, but if we change that, it's going to go to 2 kilohertz, and now it's detecting that over here, and these are dark. So if we hit it again, we go back to continuous wave, and then we'll go to 270 again, and then we can see it on the 270 light. So again, the limitation on this, and we'll put this under the test and get out a spool of fiber, but the limitation is, as long as this can read the light, whether it's 50 kilometers, 20 kilometers, whatever, you could use your light source to verify you're on the correct fiber by changing the modulation of the light source. That, in essence, identifies or could tone out, for intent and purposes, the fiber that you're going to splice. Okay, so this is the other one. This doesn't have the little display in it, but what it does have is a really annoying beep. So definitely lets you know if there's traffic going on there. And then again, as we go through and cycle through our modulated light, the little indicator lights up. Doesn't change the beep or anything, so it doesn't really matter. But it does show the direction of traffic. If we were to turn this around, if we turn it around, it would show that the traffic's going the other way, all right? So again, you know, I mean, if you're out in the field and you're not sure what's in and out, just because it's telling you that that's where it's coming out at really isn't necessarily true, right? So, you know, obviously it's still coming out of this side, which means that the light's flowing that way. So you just got to be careful when you're using these. Now the other one, the final one that we have is this guy. And this guy, you don't have any little sleds or anything. You just kind of pop it down in here, get it seated in there. Pull the trigger. Oh yeah, got to turn it on. Pull the trigger. This guy has the display. It shows you an estimated, some kind of dB number that, you know, again, Harley-Davidson gas gauge, entertainment purposes only, shows us that we're doing 2 kilohertz, which matches this. This 1550 is a little confusing because we see 1550 here. That is what the wavelength is here. And that is for the power meter. But again, you know, as we go through our modulated light, so we got 270, it just gave us a little beep, 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 1 kilohertz, and 2 kilohertz. So kind of the best of both worlds. You get the beep, but it's not annoying because it's not continuous, and then you also get to see some kind of number and that there's traffic on there. So again, this is a nice little unit. I like it. When you're using these guys, LFIs, LFDs, one of the other considerations, the type of fiber that we're testing or that we're using this on, as we've covered it, I believe we've covered it in the video, is the different classes or types of ITU fiber. The G.652, 657, 653, 655, all this wonderful stuff. These are all very application-specific fibers that are manufactured, you know, with a non-zero dispersion shifted, zero dispersion shifted, bend-in sensitive, standard type of fiber, things like this. And they, you know, some of it's used in long haul, some of it's used in metro. You know, there's all kinds of different things. So when you're testing, the newest type of fiber is G.657 ITU. It's a G.657, and there's different subclasses, so the A, the B, C, D, etc. This is fully compatible with G.652, so if you were splicing this into a G.652 cable, it would be fine, all right? This guy here, this is what's called bend-in sensitive fiber. And so they use, when they manufacture it, they use what's called an optical trench. And again, I don't want to get too in the weeds on this, but if it's something that you guys might be interested in, we can have a discussion on the different types of fiber, the different methodologies of manufacture, etc. But they do what's called an optical trench. And basically it's for lack of a better term and easy explanation, you have a core, you have a cladding, and in between that, and those are different IORs, indexes of refraction, so they have different transmission properties as far as the speed of light. And in between there, they put in another layer. So what happens is as the fiber bends, the macro bend, what happens is the light comes up, hits a critical angle, and disappears out the side. Well, that trench will come up and it will hit that and make it reflect back into the primary core, and so it's less sensitive to bending. Where you find this is in these kind of things, right? So this is, you know, this is a hardened drop. This is something that you might find in, you know, doing your pond installations. It's a push fiber, some folks call it. This is G.657 because you're going into a premise and you might be going around corners and, you know, around the baseboard, etc. And so it's going to be very prone to macro bends. Again, these guys work on a macro bend, and sometimes, you know, depending on the type of fiber that you're testing, they may not actually work well on a 657. So this guy here, in this short, so this is 1 kilometer, he's already down, putting this macro band in down at neg 57, so pretty low. He is working, but again, I don't know, I don't have any data on, if this only measures down to, let's say, negative 70, and you've got 20 kilometers of fiber, and this light is launching at, again, a minus, let's get this back over here. Get it off modulation. So this is minus 54, and we're launching at a neg 7. Well, in your pond, you might be, if you're testing post-splitter, so after the splitter, and you've got, 15 dB a drop there, plus your fiber, so you're down at neg 20, neg 18, that light might not be high enough to be read. So we'll go ahead and just take and put in our coil of fiber, spool, and see what happens and how far we can actually go out and see the modulated light. Be right back. Okay, so as I was getting my spool of fiber out, I was just thinking about this, and for illustration purposes, this is the G.657 fiber on this side, and then coming out of our light source is G.652, which is not bend insensitive. So on this side, on the G.657, we're getting negative 51, and if we just come over here, get out of there, filthy animal. Now, if we come over here and go on to the 652 side, we're getting a minus 30. So again, that's what, 22 dB. So every time, again, we lose 3 dB, it's half the power. So, it's gone from 3 dB is 50%, 6 dB is 25, 9 dB, again, you get the idea, is 12.5%, 6.25%, so on and so forth. So if you do the math, I mean, that's a huge drop between this side, and we're only going through our only contributor. Theoretically, if we were measuring pure loss, would just be this mated connector pair, which would probably be, quarter to half a dB max. So again, you can see the difference in the reading between the G.657, how much light is maintained in the fiber versus the G.652 fiber. All right. Okay, let's get our spool in here and see what we got. We've done all our calculations. We have about 8.8 engineered or estimated measured loss through our whole little network here. We're launching at a minus 7 dBm. We've got a minus 12.75 dBm over here. So our loss in all of this, including our 2 mated pair connectors, is 5.75 dB, right? The difference between the neg 7 and the neg 7.5, 12.75. Okay, so we'll take this, and we're going to go ahead and measure now. Again, we're getting a neg 6, a negative 60, and it's going low, negative 60 going low. So we're probably right at the boundary. This guy here says nothing about traffic on it, whereas if we went over to the other side here, let's get to this side, and this is on the opposite side of, this is G.657, this is G.652, we're reading a neg 29, and it states that there's traffic on there, right? So again, when they say that a VFL or a LFD won't work on G.657, not necessarily correct. It will work sort of. I mean, it just depends on where you're at in the network. So this is a push drop. It's got a protective jacketing on it, so it's pretty stiff. Now, we did want to see if we could read or use our VFL on there, put it on, and actually did a kind of a indent, a crease into the jacketing, and gave us a weak point in the jacket. Now, we tested this and it's still fine. So don't ever try to use a LFI or LFD on a hardened drop. Okay, this is considered hardened because it has a sealed connector on this. Okay, that goes into your MST. Anyway, that's that. I mean, you know, it's kind of interesting. Again, we're taught that we're told that the live fiber identifiers may not work on G.657, and again, it's going to depend on light levels and things like that. So, if you were testing this, and this was a customer jumper going into the house, it was 657, and you're sitting down at a neg 29. Yeah, I don't think it's going to work. I mean, we were only at a neg 15 dBm. You know, it did work at this level, but you drop that another 10 dB, and you know, it's probably not going to work. So anyway, I hope the discussion's been useful. Again, just to reiterate, these guys are not test equipment. These are merely identifiers just to tell us that there's traffic on there and that we should call the knock and make sure that that we're not taking out a service that has SLAs on it and fees and all kinds of cool stuff. So we hope you found this conversation useful, and if you have any questions or would like to see videos on any other topics that you have questions about, feel free, drop us a line. Always happy to do some exploring and some mad scientisting here to see what we can come up with and basically prove theories or verify what you've been told, right? So again, one of our teaching points is, you know, trust but verify. If you hear something that doesn't make sense, feel free, drop it in the comments, give us a shout on email, you know, whatever. All right, we're always happy to help you folks. That's it. So until next time, thanks for subscribing, and we'll see you on the next video. Thanks for watching.